China just spent over $1 billion on glass. Not on transistors, not on lithography machines, not on the advanced chip manufacturing equipment that Washington has spent years trying to block. On glass. And that single bet may have just made every advanced chip factory on Earth obsolete. Most people have no idea this is even happening, which is exactly why it is the most important story in the semiconductor war right now. Because the craziest part is not what China built. It is what China understood that everyone else completely missed. Welcome to Big Check Energy. The wrong battlefield for the last several years. Washington has been running what it believes is the perfect strategy. Block China's access to the machines that print advanced chips. Starve the supply chain at the source. No machines, no chips. No chips, no AI. No AI, no dominance. Clean, simple, and on paper, completely airtight. The machine at the center of that strategy is built by a Dutch company called ASML. Their extreme ultraviolet lithography systems are the only tools on Earth capable of printing the most advanced transistors onto silicon. Each one weighs as much as 2 fully loaded school buses. Each one costs close to $200 million. Roughly the price of 17 F-35 fighter jets for a single piece of manufacturing equipment. So when the United States pressured the Netherlands into restricting ASML exports to China, the logic was sound. Cut the artery. Watch the patient weaken. Here is what that strategy completely missed. It only works if advanced transistors are the only path to semiconductor dominance. And China decided, quietly and very deliberately, that they are not. Think of it this way. Your opponent has locked up the world's only supply of racing tires. Most people would spend years trying to reverse engineer the tire. China looked at the track instead, and then built a completely different vehicle, designed for a completely different surface. One your opponent's tires were never meant to handle. That surface is called advanced packaging, and the vehicle is glass. Why plastic is failing to understand why glass matters? You need to understand what is quietly breaking right now inside the most powerful AI chips ever built. The most advanced AI processors today are not single chips. They are clusters of smaller chips called chiplets, wired together on a shared platform called a substrate. The substrate is the foundation everything sits on. It carries electrical signals between chiplets, manages heat, and holds the entire system together. Right now, that foundation is made of organic material, essentially a very sophisticated form of plastic, and it is beginning to fail. A single advanced AI processor package today can stretch beyond 8,000 square millimeters. Across that entire surface, billions of microscopic connections communicate simultaneously, all of them generating heat, all of them depending on the substrate beneath them staying perfectly still. It does not stay still. Organic substrates expand and contract with every temperature cycle. Every time a chip powers up, heats, and cools back down, the substrate moves. Not visibly. We are talking about shifts measured in parts per million. But at the scale of modern AI packages, parts per million is not a rounding error. It is a catastrophe building in slow motion. Those microscopic connections, some finer than a strand of human hair, begin to drift. Slowly at first, then faster, until the electrical path between two chiplets that was once clean becomes inconsistent, degraded, and eventually broken. The industry knew this was coming. The question was never whether organic substrates would hit their limit. The question was who would have the replacement ready when they did. What glass actually does you have almost certainly held the answer in your hand? Not in a chip lab, in your kitchen. A borosilicate glass dish survives dramatic temperature swings without cracking, without warping, without losing its shape. Pull it from a 400-degree oven and set it on a cool countertop and it holds. That thermal stability is not an accident. It is a fundamental property of the material itself. Now scale that principle down to something thinner than a human fingernail, engineered to tolerances so precise they can only be verified under specialized equipment. And you begin to understand what semiconductor-grade glass substrates actually are. The list of advantages over plastic is not marginal. It is structural. Where organic substrates expand and contract with heat, glass holds its dimensional shape with the rigidity of steel. Connections printed onto its surface stay exactly where they were placed through power up, through full load, through cool down. No drift, no degradation. Then there is connection density. Today's best organic substrates support a certain number of electrical connections per square inch before signal interference makes packing them tighter impossible. Glass supports up to 10 times that density. 10 times. The difference between a 2-lane road and a 20-lane highway carrying signals between chiplets at the speeds modern AI demands. And signal integrity improves at the same time. Organic materials absorb and scatter electrical signals as they travel. Glass does not. The signal that enters one side arrives at the other side cleaner, faster, and with less interference. A better foundation that makes every chip sitting on top of it better. That is the unlock. Why nobody solved it first if glass substrates are this much better? Why has nobody built them at scale before? Because the manufacturing challenge is brutal. Picture drilling thousands of holes, each thinner than a strand of human hair, perfectly vertical, perfectly parallel, perfectly spaced through a sheet of glass the thickness of a fingernail, without cracking it, without introducing a single invisible fracture that reveals itself months later under operating stress. Then filling each hole with copper bonded precisely to the glass interior, knowing that glass and copper expand at different rates under heat, and that any imprecision at that interface creates a failure that looks clean until it suddenly is not. Early pilot lines were producing yields so low that the cost per usable substrate made commercial deployment completely impossible. You cannot build a supply chain on a material that fails more often than it succeeds. Qualification with semiconductor customers adds another 2 to 3 years. During that time, the capital is deployed, the engineers are committed, and the line generates almost no revenue. That combination of brutal process complexity, punishing yield challenges, multi-year qualification timelines, and enormous upfront capital is precisely why most Western companies treated glass substrates as a long-term research project. Interesting, important eventually, but not urgent. China looked at those same barriers and saw something completely different. It saw a moat it could afford to cross before anyone else arrived at the water's edge. China's unfair advantage here is what most analysts got completely wrong about China's position in this race. They assumed China was starting from scratch, pouring money into a new technology it had never touched, hoping state investment alone could compress decades of learning into a few years. That framing is wrong. China is not starting from scratch. China is redirecting. There is a company called BO. Most people outside the display industry have never heard of it. Inside the industry, it is impossible to ignore. BO is one of the largest manufacturers of display glass panels on Earth, producing the screens inside televisions, monitors, tablets, and smartphones at a scale so vast that a single BO campus covers more floor space than many international airports. To produce display glass at that volume, BO has spent years building and refining exactly the kind of precision large-format glass handling infrastructure that semiconductor-grade substrate production requires. Precision glass cutting at massive scale, flatness control across large surfaces, high-volume process lines where dimensional tolerances are measured in micrometers and yield is tracked obsessively because a failed panel is a direct hit to margin. The equipment categories are different. The end product is different. But the manufacturing discipline, the process philosophy, and the capital infrastructure are directly transferable. Western analysts were watching China's chip fab. They were tracking wafer starts and lithography tool purchases. They were not watching the display halls in Chengdu and Hefei, where the industrial capability to pivot into glass substrate production was already running at full capacity. That is the unfair advantage nobody saw coming. The billion-dollar bet since 2023. China's national semiconductor investment funds combined with direct corporate investment have directed over $1 billion into glass substrate technology, not into basic research, into production-oriented engineering, yield improvement, process qualification, and the supply chain infrastructure needed to support commercial volume. Investment at that scale, directed at that specific problem, with that level of state coordination, does not happen because someone found an interesting paper at a conference. It happens because a strategic decision was made at a level above the companies themselves. That decision appears to have been made around 2022. the exact moment Western governments were congratulating themselves on the ASML export restriction. While Washington was locking the front door, Beijing was funding a completely different house being built around the corner. Here is the zoom out. The next generation of AI will not be decided by who prints the smallest transistor. It will be decided by who owns the foundation those transistors sit on. Every AI model, every data center, every autonomous system built in the next decade will run on chips. Those chips will run on substrates. And if China owns the substrate, locks in the customers, and builds the knowledge moat first, then it does not matter who designs the chip. The foundation belongs to Beijing. That is what $1 billion in glass actually bought, not a product. A position. The West did not miss a research paper. It missed an industrial mobilization. And the window to respond is closing faster than most people realize. Do you think the West still has time to close this gap? Drop your perspective in the comments below. If this changed how you think about the chip war, hit the like button and subscribe so you never miss what we cover next. We will see you in the next